Imagine a tiny star, hotter than the sun's core, right here on Earth. For 70 years, scientists have chased this dream: limitless clean energy from nuclear fusion. They've spent billions of dollars, built colossal machines, and achieved incredible breakthroughs. Yet, despite all this effort, humanity still hasn't created a self-sustaining fusion reaction that generates more power than it consumes. Why is this challenge so incredibly difficult? Everything is a system. In this grade 10 lesson, we'll explore the complex dance of physics and engineering required to harness the power of a star, understanding the inputs and outputs that make fusion energy a monumental systems challenge. To understand this monumental task, let's talk to Dr. Anya Sharma, a lead plasma physicist at the Princeton Plasma Physics Laboratory. Dr. Sharma explains that fusion works by forcing light atomic nuclei, like deuterium and tritium, to combine, releasing immense energy. But to do this, we need to create a plasma, an ionized gas that's over 150 million degrees Celsius, 10 times hotter than the sun's core. No material can contain something that hot. That's why we use powerful magnetic fields to create a magnetic bottle, suspending the superheated plasma without it ever touching the reactor walls.
Whoa, what? You can get that in there with cross OBC CH.
However, every fusion reaction also releases a high-energy neutron, which escapes the magnetic field and bombards the reactor's structural components, leading to damage over time. This challenge involves balancing extreme temperatures, powerful magnetic fields, and the long-term integrity of materials. Building a star on Earth involves 9 critical components. Our external inputs are plasma temperature, magnetic containment, and fuel injection rate. These are what we control from the outside. The internal outputs are energy output, neutron damage, cooling system, power conversion, materials degradation, and net energy gain. Each of these plays a vital role in determining whether a fusion reactor can actually power our world. Let's look at how these components interact. First, there's a strong positive relationship between plasma temperature and energy output. The hotter the plasma gets, the more fusion reactions occur, leading to a dramatic increase in the energy produced. However, this higher energy output then has a positive relationship with neutron damage. More fusion reactions mean more high-energy neutrons bombarding the reactor walls, significantly accelerating wear and tear. This neutron damage, in turn, has a positive relationship with materials degradation. Over time, this constant bombardment weakens the structural materials, making them brittle and prone to failure, which could eventually limit the reactor's operational life and safety. Build your fusion energy challenge model. What if we can increase magnetic containment by 20%? How would that impact our net energy gain? Or what if new materials could reduce neutron damage by half? How would that change the operational lifetime of a reactor before materials degradation became critical? The journey to fusion energy is creating exciting career paths. Plasma physicists earning between $90,000 and $180,000 per year study the superheated gases and design the magnetic fields that contain them. Then there are fusion materials engineers who focus on developing and testing advanced materials that can withstand the extreme conditions inside a reactor, with salaries typically ranging from $80,000 to $150,000 annually. Everything is a system. Model it, build it, simulate it, understand it. Visit ModelIt K12.com.